All right, today we're going to unpack one of humanity's oldest and, frankly, most brilliant adversaries. It's a disease that shaped our history, and its biology, well, it's absolutely fascinating. So let's get into it. Imagine this. For literally centuries, people thought the waves of sickness and fever were coming from the air itself, a kind of poisonous fog, or miasma, rising from swamps and marshlands. They called it bad air. But the real culprit wasn't in the air at all. Turns out it's something much smaller and way smarter. A tiny, single-celled parasite that carries out what can only be described as a biological heist, and it's a masterpiece of evolution. So let's start there. That name, malaria. It literally comes from the Old Italian malaria, which, you guessed it, means bad air. It's like a fossil in our language, a perfect reminder of that ancient misunderstanding before we ever had the tools to see our true enemy. Okay, let's meet our microscopic villain, the Plasmodium parasite. Now, this isn't a virus or a bacterium, it's a protozoan. And while there are a few species that infect humans, there's one you really need to remember, Plasmodium falciparum, because that one is by far the most dangerous of the bunch. So, how does this parasite pull it off? It's not simple. Its survival relies on an incredibly complex strategy, a sort of two-act play that absolutely requires two different hosts to complete its life cycle. Us, humans, and a very specific type of mosquito. And here it is. You can think of this as the parasite's master blueprint for the heist. The whole operation needs both of us. We humans are the intermediate host, where all the real damage and sickness happens. But to actually reproduce and keep the whole scheme going, it needs the female Anopheles mosquito, its definitive host. So let's follow the plan step by step. The break-in starts with a single mosquito bite. That's the moment it injects these little torpedo-shaped invaders, called sporozoites, right into our blood. They're incredibly efficient, racing through our system and finding their first target, our liver cells, sometimes in as little as 30 minutes. It's a completely silent invasion. Once inside our liver cells, the parasite basically sets up a factory to build its army. Each one of those initial invaders multiplies into thousands of new soldiers, called merozoites. Then, after about a week, the liver cells are forced to burst open, releasing this massive army into the bloodstream. And the wildest part? During this whole secret amplification phase, you feel absolutely nothing. Now here is where it gets really clever and kind of terrifying. Some of the species can leave behind sleeper agents in the liver. They're called hypnozoites. They are, for all intents and purposes, biological time bombs, just hanging out, dormant, for months or even years, before suddenly waking up and launching a whole new attack, long after you thought you were in the clear.
Okay, so the parasite's army has been secretly built and released from the liver. Now the main assault begins. This is the blood stage, and it's where the parasite finally makes its presence known in the most brutal way, with the classic symptoms we all associate with malaria.
Once they hit the bloodstream, those merozoites start invading our red blood cells and multiplying again. But here's the key. They do it in sync. Millions of infected cells rupture all at the same time, releasing a new wave of parasites and a flood of toxins into your system. This synchronized explosion, happening every 48 or 72 hours like clockwork, is what causes those violent cycles of bone-rattling chills followed by a raging fever. So why is P. falciparum so much more deadly than the others? It has a nasty trick up its sleeve. It actually changes the surface of the red blood cells it infects, making them incredibly sticky. These sticky cells then start gumming up the works, creating tiny blockages in the small blood vessels of your brain, your kidneys, your lungs, starving them of oxygen and causing all sorts of catastrophic damage. And you can even spot its signature calling card under a microscope. To make its getaway, the parasite creates these special sexual forms called gametocytes. And while other species make round ones, falciparum makes these unmistakable crescent-shaped ones. This is the package a new mosquito needs to pick up to get infected and carry the heist to its next victim. The fallout from this attack can be just devastating. All that red blood cell destruction leads to severe anemia. Those blockages cause organ failure. When it happens in the brain, it's called cerebral malaria, which can cause seizures, coma, and permanent brain damage. This disease can and does systematically shut the entire body down. Okay, so we're dealing with an incredibly sophisticated and dangerous enemy here. Which leads to the obvious question, How on earth do you find it? How do doctors perform the forensic investigation required to prove this parasite is in someone's system? You know what? The symptoms can look like a lot of other things at first, so you need hard evidence. How do you actually catch this microscopic culprit red-handed?
The answer, even with all our modern tech, is still the gold standard: a good old-fashioned blood smear under a microscope. It's a two-step process. First, a thick smear, which is a concentrated drop of blood, just to see if parasites are there at all. Then, a thin smear, which lets a lab tech look at the individual cells to identify the exact species that's causing the trouble.
And that identification part is absolutely critical. It's like forensic work. A skilled technician is hunting for clues like the ones you see here: the shape of the parasite, which red blood cells it likes to infect, those crescent shapes we talked about. Getting the species right is everything because it tells you which drugs to use and how high the risk of severe complications really is. All right, so we've identified the enemy. Now, how do we fight back? This brings us to the global counteroffensive, a massive, multi-front war against both the parasite and the mosquito that carries it. Our arsenal has a few key weapons. For treatment, we have powerful drugs called artemisinin-based combination therapies, or ACTs. For prevention, things as simple as insecticide-treated bed nets have been huge game changers. But here's the catch. This parasite is a master of evolution. Drug resistance is a constant, looming threat, which means we're in a never-ending arms race. But there is new hope on the horizon. And it's the weapon we've been working towards for decades: a vaccine. The strategy behind it is just brilliant. Instead of trying to find one silver bullet, scientists are creating vaccines that launch a coordinated three-pronged attack on the parasite at different vulnerable stages of its life. And this chart shows you how that works. Think of it like this. Some vaccines try to stop the parasite at the front door, to prevent you from ever getting infected. Others are designed to fight it in the blood, to reduce how sick you get. And some have a fascinating goal. They try to stop an infected person from being able to pass the parasite back to a mosquito, breaking the chain of transmission for an entire community. And this incredible work has led to a moment that is nothing short of historic. For the first time in history, the World Health Organization has officially recommended malaria vaccines for widespread use in children. This is a monumental landmark, a genuine turning point in a fight that's been going on for centuries. So, after this whole journey, from bad air to cracking the parasite's genetic code, we finally have a new, powerful tool. But we have to remember who we're up against. This is an ancient foe with a proven, astonishing ability to adapt and evolve. So as we roll out these new vaccines and drugs, the billion-dollar question remains: what's the parasite's next move in this incredible biological arms race?